Okay, we continue with the exercises. So 10, let H be a real Hilbert space and let T in LH be compact and self-adjoint. Then H admits and H be a separable real Hilbert space, then H admits an orthonormal basis of eigenvectors of H of T and the variational characterization holds. So if you are dealing with a self-adjoint operator, then of course it means that all the everything is true. Okay, so the solution, we can show that sigma t in fact is contained in MM, where M is the inf of Txx, norm x equal to 1 and capital M equals sup of Txx, norm x equal to 1. Okay, so this did not require anything about the complex vector spaces, and therefore this you can show, and that M and capital M belong to sigma t. So this part continues to be true even in the real case because we did not use anything. Now if you go through the proof of the theorem for the structure of the orthonormal of the basis of orthonormal basis of eigenvectors, then you remember that there was a space F and we showed that F perp was equal to 0, and this was based on the fact that if you have T is sigma T equal to 0, then this implied that T equal to 0, and this was because of the fact that if M and capital M are 0, then Txx equals 0 for all x, and that required the complex structure of the Hilbert space to show that T equal to 0. But if it is self-adjoint, we don't have to do it, because for all x and y we have 0 equals T of x plus y, so that is Txx, that is 0, Tyy is also 0, and therefore that is Txy plus Tyx. So we are showing that Txx equal to 0 for all x implies T equal to 0. So if we prove this, then all the rest of the theory which we have proved so far will work. But this is nothing but Txy plus Ytx, because T is equal to T star, and that's equal to 2 times Txy, and this is 0 for all x and y, so this implies that T is identically 0. Okay, so therefore the entire theory which we developed for compact self-adjoint operators, the existence of orthonormal basis of eigenvectors and the variational characterization, everything goes through, and therefore we have this proof. Okay, so now we are going to do a series of exercises which are very interesting, and okay, so 11, V Banach and T in LV compact. Let L L and M be closed subspaces of V such that you have M is strictly contained in L. Closed subspace. Okay. Also assume further that I minus T of L is contained in M. So the bigger space, if you apply I minus T, it falls inside the smaller space. Then there exists X in L such that norm X equal to 1 and norm of Tx minus Ty is greater or equal to half for all y in L. Solution. So this smells very much like the Rees lemma, and in fact we are going to use that. So M is strictly contained in L, M and L are closed subspaces. So ML closed. So Rees lemma implies that there exists X in L, norm X equal to 1 and D of Xm is greater or equal to 1 minus epsilon, which we are going to take as equal to half. Okay. So if you take y in M, that's of course contained in L, and this implies that y minus Ty belongs to M, and this implies Ty belongs to M. So this implies that I minus so T of Ty belongs to M. Okay, fine. And if you take an X is in L, implies X minus Tx belongs to M as well. Okay. So we have Tx minus Ty equal to X minus Ty minus X minus Tx. This belongs to M, this also belongs to M, and therefore this is equal to X minus W, W in M, and therefore norm of Tx minus Ty is greater or equal to 1/2. So that proves this proposition, this problem. Okay, so now we are going to do an important exercise. So V Banach and T in LV compact. A. For every n in N, show that I minus T power N is a compact perturbation of identity. So this is a very trivial solution. Okay, so I minus T power N, apply the binomial theorem. This is I minus NC1T plus NC2 T square plus etc. plus minus 1 power N T power N. Okay, and that's equal to I minus NC1T minus NC2 T square plus etc. minus 1 power or minus 1 power N plus 1 T power N. Now T square are all compact because T is compact, so all sum of compact operators is compact. So this is equal to I minus Sn compact. So that is done. Okay, B. So let Nk equals I minus T be the null space of I minus T power k. Then Nk is an increasing sequence of finite dimensional subspaces which is stationary. That is, there exists an M such that Nm equals N, M plus 1 equals N, M plus 2 and so on. Okay, so this is what we want to show. Okay, solution. So I minus T power k equals I minus Sk, Sk compact, So null space of I minus t power k equals nk is finite dimensional. We have seen this, it's the Ries-Fredholm theory. Okay, and also I minus t power k of x equal to 0, so x is in nk. This implies that I minus t power k plus 1x is also 0, so this implies x belongs to n k plus 1. So nk is always contained in nk plus 1 for all k, and therefore it's a increasing sequence. So we want to know that if this is stationary. So assume for all k, nk is strictly contained in nk plus 1, that it never misses. Now all finite dimensional spaces are closed, and you have the strict inequality. So by 11, exercise 11, you have, there exists, oh yeah, we have to check before we can use 11, we have to check one term. So let x belong to nk plus 1. Okay, so I minus t to the k plus 1x equal to 0, and therefore you have I minus t power k of I minus t x equal to 0, that is I minus t of nk plus 1 is contained in nk. So the bigger one, so this is exactly the situation you have for exercise 11. So by exercise 11, there exists xk in nk such that norm xk equal to 1, and the distance of xk from nk minus 1 is greater or equal to 1/2. So sorry, we had it better. We have norm of txk minus ty is greater or equal to 1/2 for all y in nk, and this means that norm of txk minus txj is greater than 1/2 for all j less than k, and this is a contradiction since t is compact. So you have a bounded sequence with norm 1, and this implies it cannot have a convergent subsequence, and therefore so implies there exists an m such that you have that nm equals nm plus 1. Okay, but then we want to show it is constant thereafter. So nm plus 1 of course is contained in nm plus 2. So let x belongs to n m plus 2. Then I minus t to the m plus 2 x equal to 0. That means I minus t x belongs to n m plus 1, but nm plus 1 is the same as nm, and therefore you have I minus t to the m plus 1 x equal to 0, because I apply I minus t, this belongs to, okay, so I apply I minus t power m to this, it's 0, that means I am saying this means x belongs to nm plus 1. Therefore nm plus 2 equals nm plus 1, and thus n L equals nm for all L bigger than m. Okay, so the sequence becomes stationary. C, if V is a Hilbert space and T is self-adjoint, show that m equals 1. Okay, so very first step it will happen. Okay, so we have n of I minus t is of course contained in n of I minus t square. Okay. So now let x belongs to n of I minus t square. So I minus t square x equal to 0. So I minus t square x equal to 0. Now you take one I minus t, the I minus tx, I minus tx equal to 0, since t equals t star. Okay, when I take the adjoint, and that is norm of I minus tx square equal to 0 implies x belongs to n of I minus t. So the two are equal. So n of I minus t equals n of I minus t square, and thereafter all of them have to be equal as we have just seen, and therefore m equals 1. So in the self adjoint case it is immediate. Okay. Then D, V Banach M T in LV and M as in B. So that is the level at which the null space becomes stationary. Okay. Okay. Define Fk equals range of I minus t power k. Then Fk is a sequence, decreasing sequence of closed subspaces. Further, Fl equals Fm for all L bigger than M. The solution. So I minus t power k equals I minus sk, sk compact. This implies that Fk is closed. Range of is always closed. Okay. So so if y belongs to Fk, y equals I minus t power k x, which is equal to I minus t power k minus 1 of I minus tx, and therefore this belongs to range of I minus t to the k minus 1, which is equal to Fk minus 1. Okay. So Fk is always contained in Fk minus 1, so it is a decreasing sequence. Now T compact implies T star is also compact, and therefore there exists a P such that n of I minus T star L equals n of I minus T star P for all P L bigger than P. But dimension of n of I minus T star L is the same as the dimension of I minus T power L. Okay, so this is, we also know that because they are adjoints of each other, and therefore the dimensions of the null space are the same as we have already seen, and this implies therefore that P equals n. Okay. So for all L bigger than M, you have n of I minus T star power L equals n of I minus T star power P, power M, sorry. Okay. And now if you take the orthogonal, so this implies n of I minus T star power L perp equals n of I minus T star power M perp, and that is nothing but range of I minus T power L equals range of I minus T power m for all L bigger than m, that is FL equals Fm for all L bigger than E. V Banach, T in LV, compact, M as in B. Then V equals Nm direct sum Fm. So let X belong to V. Then I minus T M of X, this belongs to Fm, but that's equal to F of 2m, and therefore this can be written as I minus T power m X is I minus T power 2m of Y for some Y. This implies that I minus T power m of X minus I minus T power m Y equal to 0. So this implies X equal minus I minus T power m Y belongs to Nm, and this belongs to range of m, so this belongs to Fm, and therefore X, so V is therefore equal to Fm Nm plus Fm. So let X belong to Nm intersection Fm, then X equals I minus T power m Y for some Y, and 0 equals I minus T power m X, which is equal to I minus T to the 2m Y. So implies Y belongs to n of 2m, which is equal to n of m, implies I minus T power m Y equal to 0, which implies that X equal to 0. So this implies that V equals Nm direct sum